Good morning, students. Today I'll be starting with the module 5, that is the field effect transistors. So these field effect transistors, in short, they are abbreviated as FETs. They are also called as junction field effect transistors. They are called as junction field effect transistors or FETs. Basically, these FETs or JFETs, they are voltage control devices. That means the input voltage controls the output current. The output current of the device is controlled by the input voltage, hence they are called as voltage controlled devices. These FETs have high voltage gain and high input impedance. That is, their voltage gain is excellent and they have high input impedance. Moving on to the basics of junction field effect transistors, that is JFETs or FETs. As you can see here, this first figure is the N-channel FET. That is, the arrow is pointing inwards or towards the transistor. So it is N-channel FET. Towards the FET, it is N-channel FET. And it has three terminals: source, gate, and drain. And the voltage VDS is applied between drain and source, because of which the drain current is flowing. So the direction of the drain current is also shown here, right? Then the P channel FET, the direction is pointing away from the FET. As you can see here, the direction of the arrow mark is pointing away from the FET. So again, the drain to source voltage is applied and the drain current is flowing out from the FET. This source, gate, and drain terminals are similar to the emitter, base, and collector terminals, right? So we know that emitter current is equal to base current plus collector current. Similarly here, the source current is equal to the sum of the gate current and the drain current. Okay, so similarly in the P channel FET also, the source current, if it is flowing inwards here, then the gate current and the drain current will be moving or flowing out of the FET. Source current is flowing into the FET, whereas gate current and drain current are moving out of the FETs. So a junction field effect transistor, abbreviated as JFET or FET, is a three-terminal semiconductor device in which the current flow is due to only one type of carriers, that is either due to electrons or holes, and hence it is called as a unipolar device. FET is a unipolar device because the current flow is due to either the electrons or due to the holes. It has got its name as field effect transistor because when the external voltage is applied, the field is developed, electric field is developed, which controls the flow of current in the FET. When the external voltage is applied, it develops the electric field that controls the flow of current in the FET, and hence the name given to it is field effect transistor or the junction field effect transistor. As we have seen in the above figure, the symbols of N channel and P channel FETs. This is the symbol of N channel FET and this is for the P channel FET. In the N channel FET, the current flow is only due to electrons, whereas in P channel it is due to the holes. Here we are seeing the biasing of the FET. So the gate to source voltage is applied with, gate to source terminal is applied with the voltage VGG, and between drain to source it is applied with the voltage VDD. The drain current is flowing, VDS is the drain to source voltage, and VGS is the gate to source voltage, right? And the gate to source voltage controls the drain current. As the gate source voltage changes, the output drain current also changes, and hence it is termed as voltage controlled device. The relation between drain current and gate to source voltage is given by an equation called as Shockley's equation. So the relationship between drain current ID and VGS is given by Shockley's equation. It is ID is equal to IDSS into 1 minus VGS upon VP the whole square. This is the equation relating the drain current and the gate to source voltage. Now if this VGS is made equal to 0 here in this equation, then ID becomes equal to IDSS, right? When VGS is equal to 0, the drain current becomes equal to the IDSS, right? That is IDSS, that is the saturation current, drain saturation current becomes equal to the maximum current. It is IDSS is the maximum drain current in the FET, which occurs when VGS is made equal to 0 volts. Similarly, when VGS is made equal to VP, when VGS is equal to VP, so it is 1 minus VP by VP. VP by VP cancels, so it is 1 minus 1, it is 0. So ID becomes equal to 0. That means when VGS is equal to VP, the drain current will be equal to 0. So this voltage VP is called as the pinch off voltage. the voltage VP is called as the pinch off voltage. So this pinch off voltage VP is negative for N channel FETs and it is positive for the P channel FETs. So this is an important equation called as the Shockley's equation. Then about the features of FET. FET is less temperature dependent or less affected by temperature as compared to that of the transistor. As the temperature increases in FET, the drain resistance increases. As drain resistance increases, the drain current decreases. Okay, because of the increase in temperature, drain resistance increases, the drain resistance increases, and hence the drain current decreases. So if it is more temperature stable as compared to that of the transistor or as compared to that of the BJT. FET has high input impedance in terms of several mega ohms. The space occupied by FET is small as compared to that of the BJT, right? And hence it is used in the integrated circuits. Right? The gain bandwidth product of FET is less as compared to that of the BJT, which is a disadvantage of the FET. The gain bandwidth product is less. Right? If you plot the graph of the gain versus frequency, and if we take the product of gain into the bandwidth or the frequency, that is less as compared to that of the transistor. This is a disadvantage of the FET. So the frequency response is not that much good as that of the BJT. And it exhibits no offset voltage at zero drain current. That is, when the drain current is zero, the offset voltage is zero. Offset voltage means even if the voltage is zero or the current is zero, if voltage is zero, there should be zero current, is it not? Voltage is zero, therefore the current should be zero, is it not? So here sometimes what may happen is, even if voltage is zero, the current will not be zero, or if current is zero, the voltage will not be zero. So this is called as offset. Okay, if the voltage is not zero, it is called as offset voltage, and if voltage is zero, the current, if it is not zero, it is called as offset current. So this FET has no offset voltage. That means at zero drain current, the drain voltage will be zero. Following here, okay. And the voltage controlled resistor RD, voltage drain resistance RD, is given by R0 divided by 1 minus VGS upon VP the whole square, where R0 is a resistance, source to drain resistance, when VGS is equal to 0. Suppose if you put VGS equal to 0 in this drain resistance formula, then we'll get RD equal to R0. So what is R0 here, students? R0 is a resistance, source to drain resistance, when VGS is equal to 0 volts. So this RD is the resistance at certain value of VGS. At certain value of VGS, the whatever is the resistance of the drain, that is called as the drain resistance RD. I hope everyone are following here. Yes. JFET is a 3-terminal device. We are familiar with it now. So in N-channel FET, major part is N-type material, which forms a channel between two layers of P-type material. So as you can see here in this diagram, right, in the N-channel FET, the channel is N layer in between, which is embedded between two P-type layers, or which is sandwiched between two P-type layers. Okay, so one is a source terminal, then gate and drain terminal we have, similar to emitter base and collector terminal. The upper N channel is connected to the drain terminal, whereas the lower N channel is connected to the source terminal. Okay. So let us see the construction of the FET, how the construction is. Two P-type materials are connected together and connected to the gate terminal. So this is P layer, right? The N layer is in between two P layers. The two P layers are shorted and they are connected to the gate. Two P layers, this P layer, right, and this P layer, they are shorted and connected to the gate terminal. Now initially VGS, if we apply 0 volts, the gate to source voltage, if we apply 0 volts VGS, right, when VGS is 0, and if we are applying certain value of VDS, source to drain voltage, VDD, right, when this voltage is applied, then because of positive polarity of the drain to source voltage, the electrons are attracted towards the positive polarity of the VDS. The electrons in the N channel are attracted to the positive polarity of the VDS. So because of this, what is happening is the depletion region is formed. So you can see the depletion region here formed, right? The bulged portion is due to the attraction of the electrons in the N layer due to the positive polarity of the VDS, or due to the positive polarity of the VDD. So as the VDS is increased further, the width of the depletion region goes on increasing. So this depletion region width on both sides, on both the p-type layers, goes on increasing. It goes on bulging out, right? Then at certain value of VDS, it reaches a voltage called as VP. Okay, at certain value of VDS, there reaches a voltage called as VP, which is a pinch off voltage, wherein both the depletion regions touch each other. So this bulge portion and this bulge portion, it touches each other, as you can see in this figure. Both the depletion regions are touching each other. So because of this, the resistance is very high in the N channel, and the current flowing is very less, or it is almost zero. Okay, the current is the resistance is very high. Okay, the current remains constant. Because of this, the current remains constant, and that is why we are seeing here the current going to constant, because of the reaching of the pinch off voltage, wherein both the depletion regions touch each other, and hence the current remains constant thereafter. Okay, due to the narrowing of the channels. So increasing resistance due to narrowing of the channels. So this is the current IDSS, which is a constant current. It is a saturation current when both the depletion regions touch each other at the pinch off voltage. So the depletion region is wider near the top of both p-type materials. Yes, students. So depletion region is wider at the top portion, because electrons are attracted to the positive layer here. So naturally, the bulged portion will be more near at the top regions of p-type layers. So this is what we are seeing, the pinch off condition, where the two depletion regions touch each other at a VDS voltage equal to VP. At when VDS is equal to VP, there is this condition occurring called as pinch off condition, or so that is the two depletion regions touch each other, making the resistance very high. So this is all about the construction and working of the N channel FET, N channel FET. So in today's class, students, we have seen what is FET or JFET, basics of junction field effect transistors, that symbols of N channel FET and P channel FET, right? Then later we have seen the equation. We have gone through the equation, Shockley's equation, ID equal to IDSS into 1 minus VGS upon VP the whole square, one of the important equations. Then features of FET or comparison between FET and BJT. In examination, they may ask the comparison between FET and BJT. So you'll have to write these features or the comparison between FET and BJT. Then construction, they may ask the construction and working of N channel JFET in examination. So you'll have to draw these figures, the construction, these figures, various figures for N channel JFET, and you'll have to explain along with this graph. You'll have to explain, and then explain finally the pinch off condition, which is occurring at VDS equal to VP. Fine, students. So that's all for today's class, students. Hope everyone have understood. If there are any doubts on today's topics, please send your doubts to me. I will answer to your doubts. Thank you.